All right, welcome to This Week in Machine Learning. I'm filling in for Levi today, Taylor Miller, and it's going to be kind of the Taylor show because we have Taylor Larson joining us as well.
Yep, thanks for having me.
We're excited about that, and I hope you're all having a good week. We're going to talk about some interesting stuff today, but first let's just do a couple clerical things. Jump on, if you're watching on YouTube, we are going to do some screen sharing later. You'll want to hit the little gear in the, lower right-hand side and set up your resolution higher so you can see the small text that we're going to be showing in a little bit. You can subscribe there. That will notify you when a new broadcast is going out. Also, we would love to have you join our Slack channel, which you can get at healthcare.ai.
Yeah.
Click on Slack channel and hop in there. We've had some cool things happen in the Slack channel lately.
For sure.
You want to talk about those for a second?
Yeah. No, I'll kind of share out my screen just to kind of show that the community is so important, and kind of an error that we picked up. Did it come from the Slack channel, or just posted it? Yeah. That we ended up pulling through GitHub and fixing in the package. We had a user and a contributor that had joined the Slack channel and notified us of an error before we were able to find it and
awesome.
get it fixed and turn it right back around. So yeah, it's really cool to have that participation.
Yep. And the funny thing was that he found it, and him and I were discussing it, and sure enough, it's a real bug. And then we found it the next day.
Yeah, as I was working on a project.
It happened again. He found another thing one day ahead of us. So it's awesome. We love that kind of discovery together.
Yep.
And it will help us all make better software so that we can make healthcare better. Plug for Slack.
The turnaround, though, this guy, he's kind of setting an example, though, that quick turnaround. So as long as all of us can keep up.
Yes. Also, you put some homework assignments in the Slack channel.
Yeah, we just thought just to kind of keep everyone involved and, kind of get folks familiar with the package, I dropped in just a brief homework assignment. We have the impute column function on healthcare AI, and thought might be fun to have folks go try that out, especially as the topic for today is feature engineering. We're going to talk about handling missing data, and so I didn't know if there were any questions following that or issues, but feel free to drop it into the chat, and we'll try and take a look at it or circle back with you. So
yes,
any participation is great on that.
It's awesome. So we're excited about that. We're going to talk about a couple news things today, and then we're going to go into Taylor Larson's awesome discussion about feature engineering. First thing in the news, Health Catalyst puts on an amazing summit called Healthcare Analytics Summit. It's in September. This is the first year we're going to be offering a machine learning course. It'll be 2 days prior to the summit. You can find out about that at hasummit.com. And we would love to see some of you there to join us for our machine learning in-depth 2-day course.
Yep.
So, pretty stoked. But we found a good article to discuss today, and Taylor's got it on his screen here. It's called Applying Artificial Intelligence in Medicine, Our Early Results. So this is a company called Cardiogram, a tiny little startup in San Francisco, and they're doing machine learning on trying to detect arrhythmias. And they go over a couple points which would be great to discuss. And kind of the background for arrhythmias is 1 in 4 of us, roughly, in our lifetime will develop an arrhythmia. That's an abnormal heart rhythm.
Yeah, this coffee's not helping either, but...
Not for that,
okay.
But for other things.
Yeah.
So that kind of sets the precedent of what they're trying to accomplish. And they've kind of had some headlines go around that are pretty astonishing. And they've used some consumer-grade devices, wearables. I think they're using the Apple Watch, and they had some 6,000 participants, and they were able to train a deep neural net on, I don't know the time frame of the data, but on a significant chunk of their heart readings throughout the day, and they claim they are able to identify AFib, which is a type of arrhythmia, with an AUC of 0.97. Now that's an astonishing AUC.
Yeah.
And that means they are getting, their true positive rate is very good, and their false positive rate is very low. So that's an astonishing finding.
Yeah, probably with that amount of data coming in that frequently, and like I said, not sure how much time they collected over, but that's a pretty cool example.
It is. So there's a couple interesting things about this. One is it's proof that you can do really great work with these consumer-grade devices. These are not medical-grade devices. These are consumer-grade devices. But to do this kind of thing, it's important to discuss how important it is in machine learning to have access to labeled data. So we've talked about machine learning. There's supervised and unsupervised. Supervised is, hey, we have some label. We're trying to predict this person had AFib, this person did not.
Yep.
These are their attributes. And they kind of go into a discussion that's worth chatting about for a moment in how hard it is to find that and how important it is to get labeled data. So as we're going through a couple of these ideas, I want you to think of any of you that are working in healthcare, what labeled data sets you might have access to, and what kind of questions you might be able to answer with those, whether they're clinically relevant or they're operational or financial. We'd love to see just what you have access to and what kind of questions we could push healthcare forward with.
So without that outcome variable of did they have AFib or not, this data, while it's interesting, it may not have been, it wouldn't be useful in predicting that if you didn't have that variable to predict. Okay.
Exactly. So what they did to get that data is they actually sent, to validate that data, they sent out medical grade ECGs to people with AFib and not AFib, and that was their kind of validation set that they were able to prove the consumer devices against. So again, they talk about how hard that is. Has to do. There's been a couple of papers come out in the past few months. Google, you've probably seen the paper about predicting diabetic retinopathy as good or better than ophthalmologists, and they had to hire a team of ophthalmologists to manually classify some 100,000 images, and that's an expensive endeavor.
We were even just kind of talking about that the other day, that clinical review, that clinical validation, while it's super, super valuable data, it's not easy to come by.
Not easy to come by. The Stanford study, that's another example of where they trained a deep neural net on images of skin lesions, and they were able to get human accuracy levels on predicting skin cancers of various types. But they had to go to great lengths. They found, I think, nearly 20 data sets that they kind of glued together into one data set. That still wasn't enough, so they supplemented that with their own data from their own clinics. So think about that in terms of what data you have access to or what data you might be able to get access to, and let's see what we can do to answer some clinical questions and push healthcare forward. So that's the article. We'll slap that in the Slack channel. We'd love your thoughts on that.
Cool.
But today we're going to talk about feature engineering.
I think that plays off perfectly with the types of data we can get access to, the struggle that we go to produce interesting features. And so we'll kind of dive right into the next topic of basic feature engineering in healthcare. And I know kind of in the topic for today we mentioned how sometimes it's not always the sexiest part of machine learning. It's probably the most important part. You can produce features that really can help a pretty basic algorithm distinguish those relationships in the outcomes if you're producing strong features. And so today we're going to kind of run through just a few topics. As we had mentioned, handling missing data. That kind of goes hand in hand with that homework assignment for the impute from healthcare.ai, transforming variables in a practical way, incorporating time into your model, and then also talking about efficiently leveraging your domain expertise. And so that's probably one of the biggest components of feature engineering. While there's some automated feature engineering out there, you really can't substitute domain expertise at the moment.
And there's nothing like that. Getting in and knowing what that data means can make a huge difference.
Yep, exactly. So just to kind of level set before we dive into those four topics I mentioned, I wanted to kind of hit up a little bit of common terminology just kind of around features and feature engineering. So some of these I just pulled off the internet for definitions, just since it's kind of all what we're working from. So a feature is an individual measurable property of a phenomenon being observed. Sounds a little bit more complicated, but examples are age, gender, number of times a person has come to the hospital, or the cost of a patient's visit, things like that.
Lab values.
Yep.
Observations.
Yep. So we'll also call them variables, data elements, columns. But the feature, really becomes valuable once it's been engineered in some fashion to reduce the noise and increase the signal around that feature. So feature engineering is when you apply domain knowledge to the data to extract the meaningful pieces of it and what can actually inform the model to correctly make predictions. And then feature profiling, just kind of it's kind of a subset of feature engineering where you're diving in to see what's the availability of the data. Are there lots of nulls? Is it being well populated? How many categories are there? All those types of things to kind of do an assessment of completeness and getting an informative summary of the feature. So kind of my simplified impression of the process of feature engineering is, it's cyclical and iterative, but you start off once you kind of understand your use case pretty well for whatever project you're working on, brainstorming features. That could come from literature reviews in the past. It could come from speaking with clinicians or folks in operations or other people in the data world that are familiar with the problem and things that explain that problem. And then you really kind of want to use that brainstorm part to decide where the biggest bang for your buck is so that you go after those heavy-hitting features that are worth the lift, because it's a big process to build features, whether that's in SQL or directly in R or SAS, whatever you're using to get that data set built. And then from there, you're selecting your features, and that can be done automatically through running your algorithm and having something like Random Forest saying, these are your most important features, and so hang on to those, or that feature is not very predictive, so find something else, and then evaluating your model to see how well it does at predicting your outcome.
I'm often asked, hey, well, how do I know if I have the right number of features?
Yeah.
How do you answer that question?
Yeah, the right number of features, it's probably going to be totally dependent on how predictive each of those features are. Some features can end up proxying for several other things, so maybe that encompasses a few, or maybe you have to break one feature out into many just to get at the underlying relationship that you're after. And so, to be honest, in some of our projects, we start with 100 features and whittle it down to 20, or we start with 100 features and whittle it down to 50. It can just kind of depend also what you consider on your dummy variables to be separate features or not. But yeah, kind of with that said, on how many features you might be looking at, I took those 4 categories, and this is kind of my assessment, but also kind of what I was able to gather from other folks that are experienced with the process of feature engineering, is a huge chunk of your time is devoted to building the features. So that's coming up with those definitions, writing the SQL, producing those columns of data, and then the other pieces, the brainstorming, the selecting the features, the evaluating the model, those come pretty quickly. While they're still extremely, extremely important, they just take a little bit less load on the time. So I thought I'd just kind of provide that chart just to kind of show how important it is, also where so much of the relative effort is spent. So jumping into kind of those 4 topics now, handling missing data. We have a few different options for handling missing data, and I tried to kind of break this slide out into kind of some positives and negatives of each approach, as there's trade-offs for every decision you make in machine learning. And so one thing you can do, and that if you're not imputing in healthcare AI, you're dropping records. You're dropping records that have a null value, kind of like in this table I'm showing over to the right side of the slide, where any of those fields that have incomplete data, you could choose to drop them because they don't have everything you need to make the prediction. You don't have enough information about them. But then, of course, you drop those records in training and in when you're creating your predictions. Those ones don't get a prediction. So that may not be appropriate for healthcare. You may not have the option to not provide some sort of guidance. The other option is to reduce features. So columns that have a lot of nulls, you might want to remove those, especially if there seems to be a good reason for those ones being null. But then, of course, your model might not perform as well as if you had that column.
Yes.
So another trade-off. Third thing is acquire those missing values, and that's kind of what you're talking about with the article where they need to go out and get the information about that outcome variable.
Yes.
So they've got some inputs, they don't have the output, and that can be expensive, time-consuming, and but there's not really a negative trade-off other than those things I just mentioned, because you're getting accurate data
Yes.
to substitute into the model, and so that's one other option. Imputing values, that one is probably the most common. There's relatively low trade-off if you make precautions for it. So understanding why there's missing data. Is it missing at random, or is it missing because, say, one of your 4 healthcare facilities doesn't collect that piece of data? You need to know why it's missing.
Yes.
And if it's at random, then doing things like imputation, where you're substituting the mean on a continuous variable or substituting the mode for a categorical variable, then that's actually pretty reasonable, and helps you still make predictions on every row, not get rid of any columns, and kind of move forward, but with some definite underlying assumptions.
How have you handled cases where most often a value was missing? I think we had a case where, however, when that value was there with some rare lab test, it was very predictive.
Yeah, that's a great question. I do remember that case where this lab value, not only it being present, but then the actual value of that field when it was present was highly predictive of the outcome. So you don't want to lose that by saying 98% of the time this thing is null. So one way to do it is to turn that into a dummy variable where you're saying, is this variable present, yes or no? And then that's a telling feature. And then another option is to then say, is that value either above or below whatever kind of the clinically relevant threshold is, so that all those ones that were null, they're not above or below, they're not meeting the important criteria. So you can kind of toss those out while still keeping the rows. So
Nice.
a couple different ways to do it. Another important topic, transforming features in a practical way. So your data, you're going to have all sorts of features. In healthcare, they collect so much data, and it's not always that meaningful in its raw form. And so transforming it in a meaningful way is really important, which can include interacting values. You would do that possibly by, in this kind of tiny text example, you can see that we have height in inches and weight in pounds. You could convert that over to metric and change it to the body mass index, so that you're not trying to compare someone who is 5'4" to someone who is 6'4". You now have an interaction of their height and their weight in the form of BMI, so that it kind of level sets that field. Another one that then also, if that ends up being significant, you can toss out height and weight if they're not meaningful on their own, and reduce the number of features you're pulling through your model. Standardizing numeric variables is another option that could come in the form of something like body mass index, where you've standardized it, but then also doing like a z-score, where you're getting both kind of direction. So obese is increasing a certain outcome, and the fact that they're underweight or normal is decreasing something, or getting a relationship both directions, and then also just kind of normalizing those values across the whole population so you can compare.
So we just got a great question that I think ties
Sure.
into something you're going to talk about. But Jonas is asking, is it common practice to split a numeric feature into multiple binary features? For example, a white cell count.
Yeah.
Could we bin that into categories of, okay, greater than 300, less than, and so forth?
Yeah. So I think you could do that where already a lot of times EHRs have they put in their own high, normal, and low values, and so they're doing that same thing where there's some clinically relevant threshold that they say above this, then normal, and so yeah, you could do that. The EHR sometimes does that, or you could split those out into many kind of dummy variables that are yes, no, depending on the threshold. But that would be extremely common to do on a lot of vital signs where there's some important value, a blood pressure that drops too low or a heart rate that gets too high. Yep. So then with that said, creating categories, using this course goes to your domain knowledge of knowing what's relevant, but grouping things into categories. So going from a body mass index that's continuous into kind of those different levels of BMI.
Yes.
And that can help kind of reduce some of the noise, so you're not worried as much about the incremental relationship between each person's BMI, but more which of those categories do they belong to. And then you can further, if you have the context, you can also continue to reduce those categories into more and more meaningful groups, and then creating flags as well. So we just covered creating the categories, reducing the categories if there's some true meaning to them, and then creating dummy variables. So like in this instance, BMI, overweight or obese flag, so that you're really kind of getting at what you're trying to show. Another one is incorporating time into your model, and this one can be quite important, but also a little bit challenging. So I was just trying to think on this one. I meant to also mention on the transforming features before we go too far away from it, that healthcare AI does a lot of the dumbification of those variables. Once you've got the categories reduced down to a reasonable level, it'll create some of those dummy variables. So don't forget to kind of that feature's embedded, but just know that that's happening. And then same with incorporating time into your model. You'll notice that you can create a dummy variable with something as simple as a date, where you're not having to create all those iterations of a dummy variable, but you'd want to normalize date-time components. So instead of having these date timestamps, instead looking at things like, is this the earliest value or the latest value? Is this a highest pulse in the first 30 minutes? You're just kind of normalizing it so that you can compare those things no matter which day or year or time that a patient came in. And then seasonality, which is a great way for pulling in something like an admit date or the date that a certain test was done, so that you can account for the fact that maybe someone who comes into the emergency department on a Friday night at midnight is different from a person who's waiting in the ED waiting room on a Monday morning at 11 a.m. There could be something important about that. There also is seasonality in regards to, so that's more like seasonality in time and day. Then there could be seasonality in, the difference between coming during flu season or coming outside of flu season, and which types of patients are likely to show up during those times, and what interventions you can provide. So that kind of can tune up the model a little bit as well. This one, we could talk about for a long time, but efficiently leveraging your domain expertise. It's just so important to think critically about what you're looking at and what you're seeing in the data. And when you're building features, you can save yourself a lot of time, and you can produce a much stronger model if you're using those critical thinking skills that I feel like most folks in machine learning, most folks in data analysis have. Those are kind of some innate skills in a lot of us. So scalable architecture, this will save you some time, but reusing SQL. So if you're always looking for the min and max or the earliest and latest, or you're always looking through flow sheet data to find certain values, or always producing lab data, don't reinvent the wheel each time. Borrow SQL from before and create it in such a way that you're able to just change out like a where statement and flow through some new data, so that you can get to putting that into the model much quicker versus spending time feature engineering. And employing tools like R Markdown notebooks, where you can document some of your assumptions right along with your code, right along with the definitions behind your code, both English and SQL, or English and R scripts all right together. And that's kind of a nice way to pass on artifacts as well as you move on to different projects.
Because that can be reproducible 6 months later when you realize, oh, what was I doing when I was making these features? Oh yeah, you've got your documentation right there.
I have a hard enough time keeping my own stuff straight, let alone passing it on to other folks, or especially in a client relationship. That's a really great idea. Something we all could afford to improve on is that documentation stuff. It really does save time, even though you have to invest some on the front end. Another thing, and I had thrown together this little chart on the right side where, keeping in mind that additional data sources, there could be ways that things are documented differently, or certain subject matter experts could know something about the data. So knowing that maybe the clinical diagnosis table is not complete enough, and that you need to also, if you want to get the whole picture of people's their history of diabetes, you might need to go through the problem list, their medical history, billing and claims, because maybe there's some variation in how those things get documented, and you might be able to pick up on the whole picture. Probably another one of those things that you wouldn't know unless you have that domain knowledge. And that kind of goes straight into the caveats in the data. Highlight anomalies and outliers as soon as possible so that you can either have them explained, account for them, or dig into them deeper. And a lot of times the subject matter experts are going to be able to help with that, or even your fellow data architects, data analysts might have had experience with that exact feature, that exact problem, and we're not always that great at passing along those learnings.
Yes.
And then I feel like we say this in every broadcast and webinar, but understanding the use case, sometimes that means revisiting with the end user often so that your features are making sense to them, their use case is staying stable with what they thought it was going to be, and that way you're not building features that explain something that they don't want explained anymore.
Answer the right question.
Yeah, because otherwise it's all for naught. So yeah, make sure you're kind of focusing on that.
We've got another good question coming in from Paul saying, hey, we've got a lot of our labs send data to us in an unstructured format. What do we do?
Yeah, I'm not sure on unstructured.
That's a hard problem. It's a very hard problem in healthcare. We've got so much data in these unstructured notes.
Yep.
Eventually, we would love to see some excellent work in the NLP field where you're extracting structured data from unstructured data, but that's a hard problem. We'd love to chat more about that.
Yeah, exactly. Because there's so many ways you can go about it, and it doesn't always capture, everything. And so I think if it's really telling and it's worth the lift to parse through it, then it might be important. But I would try and understand that, understand how helpful it's going to be before you go down that path. So looking for literature around that exact value, which you may know that coming from the fact that that's how you're getting all your lab values, but that's kind of tough.
Yeah, and it sounds like we've got some on-demand webinars you can just watch on NLP and kind of the current state of where that is, and we'll post some links in Slack so you can all see that.
Yeah, because you can go as basic as searching through it with SQL to some much more advanced things that are
regexes or whatnot.
Yeah, so that.
Well, it's fantastic, Taylor. That's
kind of brings us to where we're at.
Excellent overview of feature engineering and what it is. We would love to discuss feature engineering more. Hop in Slack and let's chat about that to see what kinds of challenges you're facing when you're doing this. It's not always straightforward, and once you do it a few times, you kind of realize, okay, that's what this big scary word of feature engineering is. We're just trying to create sense in a clinically relevant way out of data that may not make sense to begin with.
Yeah. So
great.
Yeah, kind of keep going back to that, trying to pick up that signal that is pointing to the question you're trying to answer, and so just those critical thinking skills go a long ways, and then turning that into something that the model can consume in as simple a way as possible.
Definitely.
Yep.
Well, it's been great. We look forward to interacting with you next week and in between. We will see you all later.
Thank you for joining us today. Remember to like, share, and subscribe, comment below, and click the links below to join our Slack channel and our Healthcare AI community.